All right, let's get right into it. Today, we're going to tackle a classic physics problem. It seems pretty simple at first, but honestly, it reveals something really beautiful and elegant about how electric fields work.
I find the best way to really get a concept is to just see it in action. So we're going to solve a very specific problem together, step by step.
And here it is. At what distance from a point charge of 4 nanocoulombs is the electric potential 1, 2, 3, and then 4 volts? This is the central mystery we're going to unravel right now. And this is the equation that runs the whole show. V, that's the electric potential we're curious about. Q is our point charge, that 4 nanocoulombs. K is just a constant of nature. You can think of it as setting the strength of electricity in the universe. And R, well, R is the distance. That's the thing we're looking for. So, since our goal is to find the distance r, we need to rearrange this formula to get r all by itself. It's actually just a little bit of simple algebra. We start with the main equation, multiply both sides by r, and then we just divide both sides by v. And there you have it. The distance r is k times q, all divided by v. Perfect. We've got our rearranged formula. Now comes the really fun part, plugging in the numbers and seeing what we find out. Let's get to it.
Okay, so let's just lay out what we know for sure. The constant k is a huge number, 9 times 10 to the 9. And our charge q is a tiny number, 4 times 10 to the negative 9. Now, these numbers might look a little intimidating with all those powers of 10. Look what happens when we multiply k and q together before we do anything else. You've got 10 to the power of 9 and 10 to the power of negative 9. They completely cancel each other out. So all we're left with is 9 times 4, which is just 36. It makes everything so much cleaner. Our working formula is now just this. The distance r is equal to 36 divided by the potential v. So let's just run the numbers real quick. For a potential of 1 volt, the distance is 36 divided by 1, which is, of course, 36 meters. Okay, for 2 volts, it's 36 divided by 2. That gives us 18 meters. Now, hold on, did you notice that? We doubled the potential, and the distance got cut exactly in half. Interesting. At 3 volts, 36 divided by 3, we get 12 meters. And finally, at 4 volts, we land at 9 meters. So there are our answers: 36, 18, 12, and 9 meters. But what does this pattern actually mean? All right, we've got our answers. But in physics, the numbers are only ever half the story. The real insight comes from understanding what those numbers are telling us about the real world. So let's ask that bigger question. What do these distances, 36, 18, 12, 9, what do they really mean? What's the pattern telling us? So here's what the numbers are screaming at us. First, as the potential goes up, the distance goes down. That makes sense. But look closer. The jump from 1 to 2 volts was a gap of 18 meters, but the jump from 3 to 4 volts, that was only a 3-meter gap. The lines of equal potential are getting squeezed closer and closer together. You know the best way to picture this? Think of a contour map of a hill. The lines on the map show you points of equal elevation. Where the hill is kind of flat, the lines are really far apart. But where the hill gets super steep, the lines are all bunched up, packed tightly together. Our electric field is just like that hill. The higher the potential increases, the closer my lines get to each other. That's the whole idea in a nutshell. The field gets stronger the closer you get, and those tightening potential lines are the visual proof. So, I'll leave you with this one last thought, just to really lock it in. Using our super simple formula R equals 36 over V, what would happen if the potential doubled again, all the way to 8 volts? What would the distance become? I have a feeling you already know the answer. And that's the absolute beauty of physics, finding a simple rule that explains a complex world.